Welcome to the Introduction to Remote Sensing Using GIS. For this first lecture, I am going to talk about basic principles of remote sensing. So what is remote sensing? It refers to the activities of recording, observing, and perceiving or sensing objects or events at far away or remote places. This is a general definition. In remote sensing, the sensors are not in direct contact with the objects or events being observed. Here's some examples of imagery and products that were created with remote sensing. So in the upper left, we have land cover. In the middle of the top, we have a digital elevation model. On the right, we have a color-coded file showing the ocean temperatures, and it is clearly outlining the Gulf Stream. In the lower left, we have a false color image, and then on the right is a representation of some underwater bathymetry. So here is an example of imagery from the Congo Basin, and you can clearly see that there are natural features visible, and you can see the water bodies in blue, and in this example, the dry riverbeds are in light tan. So observations about remote sensing. It's a science, and it's defined as the broad field of human knowledge concerned with facts held together by principles or rules. Scientists discover and test facts and principles by using the scientific method, and this is an orderly system of solving problems. So remote sensing employs the scientific method, and it is used in many fields. Some examples are mathematics, physical sciences, biological sciences, and social sciences. So let's think about, is remote sensing an art? If we think of art as a visual interpretation of objects or images, then yes, remote sensing is an art. You have visual image interpretation that brings to bear not only scientific knowledge, but all of the experience that a person has obtained in a lifetime. So the synergism of combining scientific knowledge with real-world analysis, and that comes from experience, allows the interpreter to extract information from the imagery. Some image analysts are superior to others because they understand their scientific principles better, they're more widely traveled, and have seen many landscape objects and geographic areas, and or they have the ability to synthesize scientific principles and real-world knowledge to reach logical and correct conclusions. So, what do you think? Is remote sensing art or science? So here's an example of an image from the USGS, and it is a very beautiful piece of artwork. It is also a scientific product. And if you would like to explore the USGS image gallery, there is a link here that you can revisit on your own time. So information about an object or an area. Sensors can be used to obtain specific information about an object. For example, the diameter of a cottonwood tree crown or the geographic extent of a phenomenon, which would be the boundary of that cottonwood stand or the whole collection of those trees. The electromagnetic spectrum reflects, emits, or backscatters energy from an object or geographic area, and this is used to create digital images for the actual property under investigation. The electromagnetic energy measurements must be calibrated and turned into information using visual and or digital image processing techniques. Remote sensing is unobtrusive if the sensor passively records the electromagnetic response reflected or emitted by the object of interest. Passive remote sensing does not disturb the object or area of interest. Remote sensing devices may be programmed to collect data systematically, for example, a 9 by 9 inch frame of vertical aerial photography, and this systematic data collection can remove the sampling bias that is introduced in some in situ investigations. And in this case, in situ is referring to in the field or in the real world. Under controlled conditions, remote sensing can provide fundamental biophysical information, including XY, which is latitude and longitude, location, and the Z, which would be elevation above sea level or depth below sea level. It can also provide information on biomass, temperature, and moisture content, plus many others. These are just a few examples. The greatest limitation of remote sensing is that it is often oversold. It's not a panacea that provides all the information needed to conduct physical, biological, or social science research. It provides some spatial, spectral, and temporal information of value in a manner that we hope is efficient and economical. Human beings select the appropriate remote sensing system to collect data, specify the various resolutions of the remote sensor data, they calibrate the sensors, select the platform that will carry the sensor, and determine when the data will be collected. And they also specify how that data is then processed. So there's human method-produced error that can be introduced in all of these steps. And so we have error at the instrument, we have error at the analysis of the products, and it's important to remember these and consider them specific to each mission and all of the parameters of a project. Powerful active remote sensors that emit their own electromagnetic radiation, such as LIDAR, radar, and sonar, can be intrusive and affect the phenomenon being investigated. Additional research is required to determine how intrusive these active sensors can be. So remote sensing instruments over time may become uncalibrated, and this can result in uncalibrated data. Remote sensor data may be expensive to collect and analyze. So hopefully the information extracted from the remote sensor data justifies the expense. There are many advantages to remote sensing. In general, as for most instances, it is unobtrusive, it's automated, it can be useful for extreme conditions such as managing fires or extreme weather events or remote locations such as polar regions. It offers excellent spatial and temporal coverage. It provides real-time or near real-time observations. It's often cost-effective, and it extends our senses. So how are measurements made? Well, here are three basic examples. We have ground-based, airborne, and satellite. So in the lower left example, we have a ground-based system that is collecting weather phenomenon in a field. In the middle is an airborne flight flown by NASA, and then in the upper right is a artist's picture of a satellite sensor orbiting the Earth. With active sensors, they illuminate the subject from an artificial energy source. Passive sensors use natural radiation from the sun or another emitted signal. An imaging sensor creates a picture by scanning across a linear array of detectors while the array moves through space, whereas a non-imaging sensor measures along a transect or at a point. When we think about the orbits of remote sensing, this is the path of a satellite, and it's referred to as an orbit, and it's matched to the capability and objective of the sensor. So we're going to talk about different types of satellites. These orbits vary in their orientation to the Earth, the rotation relative to the Earth, and the altitude or the height above the Earth. So with a geostationary orbit, it's approximately 36,000 kilometers above Earth, and these satellites will revolve at the same speed as Earth's rotation. They are stationary relative to a location. So what types of satellites are geostationary? Well, for weather, communication, and things that require monitoring an entire hemisphere, we would use geostationary orbits because we don't want to have a break in the data collection or a break in service. With near-polar orbits, otherwise known as sun-synchronous, they follow a north-south orbit around the Earth. They cover most of Earth's surface in a given time. They are named for the inclination of orbit relative to a meridian line between poles, and they provide consistent illumination within a season or a short day range. These require mosaicing of adjacent images for large study areas. So what exactly does a satellite sensor see? The Earth's east-west rotation of Earth allows for new area to be sampled with each consecutive pass. And a swath is the area that is imaged on the surface. It is shown here by the dark gray band that is going down over the continent of Africa. A revisit period is the time between image collections. So satellites can view before or after orbit pass, which is off nadir to the sides. And the revisit period time is important for frequent imaging needs. If we want to consider something like an oil spill spread or flooding extent, these are events that happen very quickly, and the time of the orbit is important in order to determine which series of images we're going to analyze. So time of orbit varies with platform. So here is an example of a revisit period, and this is showing frequent collection of polar areas, and you can see that near the equator there's much less frequency of that data collection. So moving on to remote sensing data types. This is a diagram showing the electromagnetic spectrum, and we can see that there are the different types of energy from the left, gamma and X-rays, ultraviolet. Then we have visible, reflected infrared, thermal infrared, all the way down to microwave and radio, going from smaller to larger types of energy waves. And in remote sensing, we commonly use visible, infrared, thermal, and microwave portions of the electromagnetic spectrum. So the remote sensing process, the remote sensing data collection and analysis procedures used for Earth resource applications are often implemented in a systematic fashion. This is referred to as the remote sensing process. Here's a diagram showing the process. It is circular, and there are often random starting points for this cycle. So for this course, we're going to talk about sensors and the data that they collect. You are going to be performing data analysis, interpretation, and then you're going to be working with the information. You will be doing some assessment and analysis in your project. This diagram is referring to an assessment that would be done by professionals, and then the development of the cycle, which goes back, you can see, to that sensor and data. We're not going to be doing any processing of data. This is referring to the processing that's done with the satellite platform. So I'm going to step into how Landsat is made after this slide. And the reason I'm going to cover this is that the images that you'll be using in your workbook were all collected with Landsat satellites. And the workbook that we'll be using is Making Spatial Decisions Using GIS and Remote Sensing, a workbook. It's by Kiernan and Colvard, and there are 10 modules in the book. You are required to do project 1 of each module for credit. I encourage you to explore project 2 and project 3 on your own time, with the caveat that this is a quickly moving course, and once you decide on a project topic, you really should go in and do project 2 and 3 for that topic. So for instance, if you decide that you want to do NDVI, which is Normalized Difference Vegetation Index Analysis, you would want to do all 3 modules in the workbook. So Landsat, it's more than a pretty picture, and we're going to talk about how Landsat images are made. Here's an example of the Malaspina Glacier in Alaska. So what's special about Landsat? Well, the primary mission was to map Earth's land surface. The data is consistent and it has been collected since 1972. There is a 16-day repeat. This is also called temporal resolution. And there's a 30-meter spatial resolution. The data is publicly available at no cost. So the colors in satellite images represent data about the Earth. Our understanding of light makes it possible for us to design instruments that tell us stories about features and patterns on Earth and in the atmosphere. So here's an example of the operational land imager Landsat 8, which was launched a couple of years ago. So light is radiant energy. It is energy that radiates from its source. This is an example of sunlight radiating through a wilderness area. Radiant energy is emitted by all objects that are above absolute zero in temperature. So human beings have temperature, but all objects on Earth actually have a radiant energy. We measure radiant energy in wavelengths from crest to crest, and you can see two examples here. Wavelength A is longer than wavelength B. The colors that we think of that make up visible light have different wavelengths. So white light is a combination of all of the basic colors: red, orange, yellow, green, blue, indigo, and violet. And we see different colors because they have different wavelengths. Red has the longest wavelength of visible light, and blue or violet or purple has the shortest. The whole electromagnetic spectrum consists of the longest and shortest wavelengths and everything in between. And so we've grouped electromagnetic waves as radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. And this diagram is showing the relative size of things so that you can see radio waves go from about the size of between buildings and humans, and then all on down to gamma rays, which are about the size of atomic nuclei. The light that we see with our eyes alone is just a very small part of the whole electromagnetic spectrum of radiant energy in the universe. So you can see here that it is a rainbow effect, and if you've ever seen a rainbow that is light refracted through water or through a prism or crystal, it is white light that is separated out, and you can actually see those different colors with your eyes. The Earth reflects electromagnetic radiation and light of different wavelengths. We can use our understanding of electromagnetic radiation to explore Earth from space. Our exploration of Earth from space can use wavelengths beyond the visible range. So, how is this accomplished? Well, first, it helps to remember that sunlight strikes Earth's surface, and some of it is absorbed and some of it is reflected back into space. So you can see in this image on the right that the yellow arrows are representing light that's transmitted, and some is absorbed, and then there is light that is reflected. That is a scientific term called albedo. Sunlight interacts with objects, including trees and leaves. So some of the light is absorbed and some of it is reflected. Infrared, red, green, and blue light from the sun hit the tree and the leaf in this example. And then infrared and green light are reflected from the tree. The red and the blue light are absorbed. So this is why vegetation such as trees, leaves, grass appears green to our eyes, because the green portion is being reflected. We don't see in infrared, some animals do, but humans do not see or detect infrared. But you can see here by the various arrows the different parts of the spectrum that are being absorbed and reflected. We see the tree as green because the wavelengths of light we call green are reflected to our eyes by the tree. So the wavelengths that we see as green are about 525 to 550 nanometers in length, and the wavelengths we see as red are 630 to 800 nanometers in length. So this example of a red poppy flower reflects strongly at a wavelength of approximately 700 nanometers. Every kind of surface reflects light differently, absorbing and reflecting it weakly or strongly in different wavelengths. Every kind of surface has its own spectral signature. This is an example of a spectral signature graph, and it's very much like a human fingerprint, which is unique to each individual. On the x-axis, we have the wavelength in nanometers. On the y-axis, we have percent reflection. And this is showing very basic reflections of butter, tomato, and lettuce in the electromagnetic spectrum, and it's labeled blue, yellow, and red. We'll get into a lot more detail as you work through your modules, but this is basically showing you that each spectral signature has a unique curve. So here's a little bit more sophisticated example of spectral signatures. You can notice how different kinds of surfaces reflect strongly or weakly. This means that there's a lot of energy or a little energy reflected at different wavelengths. So looking at this comparison, we have at the top, we have snow and ice and clouds. We have examples of two different types of vegetation, broadleaf and needleleaf. Then we have wet soil in the middle, and then in the very bottom we have clear water and turbid water. And just notice that this graph uses micrometers rather than nanometers, and so it's important to check your units when you're looking, and it's also a log scale on the y-axis of percent reflectance. So if you consider this, you can see that the lower areas are reflecting weaker, and then the higher areas are reflecting higher. Snow and ice is at the top because it's very, very bright. It has the highest albedo on our planet, and it reflects very strongly, whereas water has a very low reflectance because it absorbs most of the electromagnetic energy. And then we have the other different types of materials in the middle. Here's an example of how technical and specific spectral signatures can be. So we are comparing here pine woods, grasslands, and then a red sand pit. So you can see that there are very precise spectral signatures that are available. And then again at the bottom we have silty water, which would be water that has a lot of suspended materials in it. So a farmer that uses remote sensing can tell which sugar beet fields are healthy and which are not, if she or he knows their spectral signatures. So this is a comparison of the green line is showing a healthy sugar beet spectral signature, and the red is stressed. Now, the stress could be coming from a pest infestation. It could be coming from soil deficiencies, could be coming from drought or water problems. But this is a tool that a farmer could use to monitor very, very large fields very quickly and determine which areas were healthy and which areas were stressed. So we measure the spectral signatures of different surfaces on the ground or in situ. And then when we look at the spectral signature of a surface in a satellite image, we can tell what kind of surface the satellite was looking at. So this is an example of in situ data collection with a handheld spectrometer. So Landsat satellites orbit Earth surfaces from space at a 705-kilometer altitude. And Landsat orbits from north to south, from pole to pole as the Earth turns underneath it. So on the left, we have a diagram here showing representative paths that the satellite would have flown over the Earth. And these are called the swaths, and the dotted line in the middle of arrows 4 and 5 is the satellite ground track. So here is a generalized pathway of light used by Landsat. So it travels from the sun through the atmosphere, it interacts with the Earth at C, it is reflected back to space and is collected by a satellite at D, and then it is sent to a collecting station where it is processed, which is shown in F, and then there is a final product which is a GIS project or a GIS output, such as a map. And then there's another satellite that is shown in here, and that is a GPS satellite, which helps keep track of very precise and specific location data for the Earth. So Landsat 5 observes the Earth in 7 ranges or bands of the electromagnetic spectrum. So you can see here it's blue, green, red, near-infrared, shortwave infrared, and thermal infrared. Please notice that the band number is not in order, and each band number is going to be unique for each satellite. So there are resources on the internet to help you find which band is correlated with which wavelength. This is just an example for Landsat 5. So in this illustration, that is an example of one band of Landsat data. Each square represents a 30 meter by 30 meter piece of land surface. So starting at the top, we have our band of, this could be a file, and then on the lower left is the pixelated view shown in shades of gray from white to black, and you'll notice that the black pixels, if you look at the numbers on the right, are very low, 0 in this example, and then the lighter ones are very high. And so in this example, it is going to 255. Now, this is based on a bit system, so it's 2 to the 8, which is 256 values. We start counting at 0, not at 1, and those numbers correlate to what would be called a DN, which is a digital number or brightness value. So Landsat has a spatial resolution of 30 meters because each of those pixels is 30 meters on one side. So the Landsat instrument records the amount of reflected light in each band for each 30 meter pixel, again on a scale of 0 to 255. The numerical value of 0 represents no reflected light, and a numerical value of 255 represents maximum reflected light. So the bright areas in an image are going to have higher DNs. Dark areas have lower. So when we put all of these layers together, this is an example of all 7 bands plus a panchromatic band. That equals a lot of data. So one of the challenges of working with remote sensing data is file management and space and disk size. So this is an example of one scene, and it is 3.8 gigabytes of data in one Landsat 7 scene. So a scene would be an area or a tile, and that will make more sense as we start working with our data. So 7 bands of data looked at side by side in grayscale, and you can see that there are slight differences. Each of these bands is representing information that was collected from a different portion of the electromagnetic spectrum. So you're going to explore how this data is displayed with color in your workbook so that it can be understood and interpreted better. So we're going to be taking these black and white pixels, and we're going to be applying color to them in order to create imagery. So remember, Landsat uses some bands of infrared light. The human eye is not sensitive to infrared light, and we can build an image with infrared data that we can see. In order to do that, we must represent that data with colors from the visible portion of the electromagnetic spectrum, the red, greens, and blues. So we have to assign colors to represent Landsat bands, and we do this using computer software. So here's an example. We've made the green band, green light, which is between 0.52 and 0.60 micrometer wavelengths, to appear red in our new image. So this on the right would be your false color image, and the green or the vegetation is showing up as red. So the analyst, which is people, can choose red, green, or blue to represent any of the wavelength ranges that they like. You can make a lot of different color combinations. These are all examples from Beverly, Massachusetts, and each of these different kinds of images would be used for different study purposes. So in the upper left, we have a true color, and then we have on the right top and the left bottom, we have false color, and these are showing Urban in the upper right is bright blue and vegetation is green. In the lower left, the urban areas are purple and the vegetation is a light green. And I think I misspoke, I'm sorry. In the upper right, the vegetation is red. And then in the lower right, it's thermal imagery, so the urban areas are showing up as bright, or what we would think of as the Earth, how it would look at night from space. So bands of energy can be displayed or combined as composites in a GIS. Here's another example of a satellite, the ETM Plus. And so here are bands 1 through 8, and again, they're not numbered in order. The numbering designation and the selection of the wavelength is done in a very complicated and long involved process by the company or organization that launches the satellite. So again, remember, whenever you're working with imagery, you need to look at your metadata and you need to know what band numbers go with which wavelengths. So in this example, band 1 is blue, and it was collected between 0.450 and 0.515 micrometers. And then if we jump all the way down to the bottom, the band 8 is a panchromatic band, and it was collected in between 0.52 and 0.90. We also have green, red, near infrared, shortwave infrared, and thermal infrared. So we can make images with different band combinations, and we can see more than we could otherwise. Here's an example of the same scene with different wavelengths. So this was collected at the same time, but as an analyst, they put together different band combinations in order to show different features of this volcano. On the left is a visible image, and you can see clearly the smoke plume, and you can see ash as showing up as dark areas in the image. On the right is thermal, and the infrared wavelengths are showing the heat and the hot spots of this volcano. So, what scientists and students can do with Landsat? Well, you can learn what's behind Google Earth and the power of data behind imagery. You can map, analyze, and predict urban growth and impervious surfaces, monitor crop health, forest health. You can measure deforestation and reforestation. You can quantify amount of land used in surface mining. You can track mountaintop removal, determine the extent of flood zones for emergency response and assessments. And this is useful for insurance claims. You can map the extent and severity of forest fires, and you can monitor seasonal wetlands to help predict the spread of pest-borne diseases. There are hundreds, maybe thousands of other examples. This is just an introduction to some possibilities. You can also estimate the amount of carbon stockpiled in vegetation. You can quantify water use on specific farms and rangelands, and you can improve forest inventories to predict tree growth and product yield. Here's an example of scientists examining the fruits of a forest tree, and satellite imagery is very useful for large areas and looking at one of the current issues facing our society, which is deforestation. That is the end of session 1, and I'm going to back up here and say a thank you to NASA for the slides that were shown in most of this presentation, and welcome to our course, and please read your syllabus and start working on your modules right away. Thank you.